Assalamu alaikum and good morning. Today we're going to continue with topic 7, equilibrium, and we are left with two sections in this topic, which is the pH titration curve and the indicator. Now, in the last lesson, I have mentioned to you briefly on the terms like titrant, which is the solution that you put in the burette. Analyte is the solution that you put into the conical flask. The endpoint and equivalence point will be a little bit confusing. We use them interchangeably, but they are, strictly speaking, they are not the same. Endpoint is the point at which your indicators start to change color, whereas equivalence point is the point where the number of moles of acid is equal to the number of moles of alkali. So this is where neutralization takes place. Okay. When drawing the pH curve, there are a few things that you need to take into account before you start sketching the graph. You need to look at the species or the analyte in your conical flask, the pH of the solution in the conical flask, and then you also need to take into account of who is in the burette. Other than that, there is this equivalence point, which is shown to you graphically, and it is usually taken as half of the vertical region. I will talk about the vertical region shortly. So just to re-emphasize on equivalence point, this is the point at which the indicator changes the color and the point at which neutralization takes place. So for your syllabus, we are taking these two terms as the same, okay? And there's also the alkaline region and the acidic region. Basically, this is area above pH 7 for the alkaline region, and below pH 7, it's the acidic region. Constructing a pH curve, you need to measure the initial pH of the acid. Well, it does not necessarily have to be acid inside the conical flask. It can be a base. And then you would add, in small amounts, you will add the solution in the in the burette in small amounts. And then you would record the pH to 1 decimal places. Okay, so this is when you are using a pH meter, all right? But in the exam, in your practical, you will be carrying this out in a normal setting where you carry out titration. Okay, so you don't have to worry about that. Now we're going to look at the titration curves. There are 4 types of titration curves depending on the strength of the acid you use and the strength of the base that you use. So for this case, in your notes, we are going to run alkali into acid. That means acid is in the conical flask. So our pH is always reading the contents inside the conical flask. So you would imagine the pH value will follow the pH of the solution in the conical flask. If you have acid in the conical flask, then your pH would be somewhere below 7. If you have base in the conical flask, then your pH would be above 7. Another thing that students tend to take it lightly is the neutralization volume. Okay, this neutralization volume is important because not only we want to know at which pH neutralization is happening, we also need to know how much volume of base is needed to be added to neutralize the acid we have in our conical flask. Okay, so students usually just assume that it's 25 centimeter cube. Now this is only possible if the number of the concentration of your acid and bases is the same and they react in a 1-to-1 ratio. Then you can assume equal number of volume would be needed to react with each other. Okay. Next, we look at the key points of a pH curve. You need to know the initial pH and the final pH. The second one is the volume of at neutralization, the one that I was just talking about. And the third one is the vertical region. Okay, so the vertical region will come naturally later on as long as you use your initial and final pH as well as your volume to guide you in sketching the pH curve. Here we have the first type of a pH curve, which is of strong acid and strong base. So the sketch will be the same for any strong acid you use to react with any strong base. Here, for our example, we are using HCl and NaOH. Now, assuming, I think in your notes, it mentions that the acid is 0.1 mole per dm cube, and we are using 25 centimeter cube of acid, and our base in the burette is 0.1 mole per dm cube. So the first and foremost that you should do is the neutralization volume or volume at neutralization. Okay. So you need to do the calculation for this. We know the concentration and the volume of HCl. So number of moles of HCl is 0.1 times, so that's concentration times volume, but be careful, your volume has to be in, I know they are the same, but I'm just going to show you the working, okay? 0.025 dm cube. So that's mole per dm cube. Okay, so it has to match. Times by 0.1, that is 2.5 times 10 to the power of minus 3. You also need to know that your acids and bases, your acid and base react in a 1-to-1 ratio. So that means the number of moles of your sodium hydroxide is the same. Now the question is, you want to find the you want to find the volume of sodium hydroxide needed for this neutralization to take place. Okay, so to find volume, you would need number of moles of HCl over concentration of HCl. And we know that our number of moles, which is the same as HCl, divide by the, why am I using HCl? It should be sodium hydroxide over concentration of sodium hydroxide. In this case, our concentration is 0.1. Okay, so you should get 0.025 dm cube, which is 25 centimeter cube. Okay, it's the same thing. Right. Okay, so if you need to copy this down, please pause this video here or take a screenshot, because when I zoom this out, it will be really, really small. Okay, so that means I need to take this into account at 25 centimeter cube, and 25 centimeter cube in my graph is somewhere, it's here. Okay, so I'm just gonna mark that for now, right? Sorry. Okay, so what happens when drawing or sketching our pH curve or pH graph, we are plotting the pH on the y-axis and we are plotting the volume on the x-axis. Okay, volume of who usually is the volume of the solution in the burette, okay, which is called the titrant. So this can be acid, this can be alkali, depending on which system you are using. So in my case, I'm putting my acid in the alkali and I'm putting my acid in the conical flask and my alkali in the burette. Okay, so right, the pH that I'm measuring is the one inside the conical flask. Okay, it would be silly to measure the pH inside the burette, right? So initially, when I only have acid, obviously the only thing that is present in my acid would be the hydrogen ions, the H plus, that is produced from the complete dissociation of my strong acid. Remember, I'm looking at strong acid. So strong acid tend to be around between 0 to 1, pH 0 to 1, okay? So I mark it like that. If you can see the blue mark, that's my initial pH. Secondly, I need to look at my final pH. All right, final pH means what happens after my acid is being wiped out and beyond. So what I'm doing is that I'm adding hydroxide from the burette, right? And it reacts with my hydrogen ions. And eventually, all my hydrogen ions will be wiped out. Okay. And then if I go beyond that, I am just transferring, I'm just adding hydroxide, sodium hydroxide into the conical flask. All my hydrogen ions have been reacted. Okay. So that means at the end, at excess volume, I am just measuring the pH of my sodium hydroxide, which is a strong base. And sodium hydroxide, strong bases in general will have really high pH, between 13 to 14, like that, okay? So you have this information. Strong acid initially starts at pH 1. Strong base would end at pH 13. And then there's the vertical region at between 3 and 11. Okay, so here's how we draw our graph. I'm gonna use, okay. So what happens is that initially, when I add sodium hydroxide to my acid, there's only like slight increase in pH. Okay, well, because of my iPad is showing is at a straight line. Okay, so let me just draw first. Okay, and I have to make sure that my vertical line is between 3 and 11. So I want, now you can memorize this. If you memorize the characteristic, 3 is somewhere there and then 11 is somewhere there. Okay, maybe I should have started with the vertical line first. And then I just draw like that. Okay, so that's easier. Draw the vertical line first. I should have prepared this earlier. Now, where is the vertical line? The vertical line has to be at the volume of neutralization, which is your 25 centimeter cube. So there are many things that you should be looking at here. Okay, so vertical line is between 3 and 11, okay, roughly. And then you just connect the line, make sure it's a smooth line. All right. So what's happening here is that as you add sodium hydroxide into your acid, it will react. Okay, so they will react until eventually you are running out of H plus. So, well, you don't run out of H plus yet, but your H plus is getting less and less. Okay, so your pH is starting to increase. At first, your increasing pH is quite gentle, and then you see a drastic change. Okay, you go from acidic region to alkali region really quick. All right, so this point or this time at this volume is where neutralization is happening. It means that all your H plus have reacted with your OH minus at the exact amount, no more, no less. Okay, and then as you go along, this is just excess hydroxide. That's why your pH value is reading above 10, above 11, okay, between 11 to pH 13. So the reason for this drastic increase is that near neutralization or near the endpoint or equivalence point, small addition of volume will cause a big change in pH. That's when you know that the reaction has completed or the reaction has ended. Okay, now equivalence point, as you all learned, is the midpoint between 3 and 11, the midpoint between the vertical region, and this happens to be pH 7. Okay, so I'm trying my best to draw pH 7 there, and that would be equivalence point or endpoint. Okay. And the equivalence point is where your H plus is equals to OH minus, sometimes called endpoint. Okay, also called endpoint for your syllabus. That's fine, accepted. So it's already explained to you that at this equivalence point, that's where your hydrogen ions have exactly reacted with hydroxide ions. No more, no less. At this region, you have more hydrogen ions than hydroxide ions. Here, you only have hydroxide ions. No more hydrogen ions left because everything has been reacted. Okay, so you can add on. This is just adding excess sodium hydroxide or any other base that you are using. Okay, let's see. What else do I need to add on here? Nothing. Okay, now, do you remember that I always tell you that when you are closer to the end point, you have to go really, really slow. This is the reason why. Okay, I repeat. So the reason why we tell you to go really slow when you are nearing the endpoint is because even the addition of the smallest volume, okay, will cause a big change in pH. So your aim is to actually be at this equivalence point or your endpoint. You don't want to miss it. If you have excess, then you're already way past the neutralization reaction. It's already after neutralization. Okay. We'll talk about the indicator later on. You essentially, since we're talking about the graph, you want your indicator to change color near to the equivalence point. That makes sense, right? You want your indicator to change color at this neutralization point because that's the only way the signal to tell you stop, the reaction has reached neutralization. Okay, so we'll talk about that later on. Next example that we are going to look at is a combination of weak acid and strong base. Again, remembering that we have the conical acid in the conical flask, assuming that the concentration and volume is also the same, so we don't have to redo our calculation. That means our volume of neutralization will happen at 25 centimeter cube. Okay. Now we have weak acid. So weak acid would have a little bit higher pH value. Since this is a sketch, you don't have to be very accurate with the pH. We can just choose something that is a little bit higher than your strong acid. Okay, so strong acid was pH 1. So weak acid, we can take 4 or 5, right? But not too close to 7. Okay, so I've got my initial pH there for my acid, and then my final pH is the pH of my alkali when it is in excess. Remembering that I'm looking at weak acid and strong base, so my alkali is a strong alkali, so the pH would be really, really high, between 13 and 14, right? So in this case, I've got my final pH to be 13. And then the vertical region, since my alkali is strong, that means my graph is shifted up. My graph is being pulled up. The vertical region will be between 7 and 11, 7.5 and 11.5. Okay, so I'm just gonna do it roughly because I am sketching. Okay, then as usual, well, that should be a straight line, nice straight line. All you have to do is just sort of connect them and make a smooth curve. Okay, so let's see. Right, so you start here and then you connect it at the start of the vertical region and then like that. Okay, right. Same thing. The same thing is happening here. Initially, your pH is slowly increasing until you are near the endpoint or the equivalence point, because that's where neutralization happens. Okay, your endpoint in this case would be between 7 and 11, so that would be around 9. Okay, so your equivalent point is here. Equivalence point, right? Notice that the equivalence point will be different in each type of reaction depending on the strength of the acid and bases that you use. Okay, but the most important thing is that we want to choose an indicator that changes color near, if not on the equivalence point, at least it's near the equivalence point. Usually anything, if the indicator changes color inside the vertical region, that's good enough for us, because the vertical region is the volume at 25 centimeter cube. So that's the volume of neutralization. Okay. Now, I forgot to mention for the previous graph, what if we had the reverse order? Our order is in reverse. This time we have alkali in the conical flask and acid in the burette. No problem with that. The only thing that's different is, since you have base in your conical flask, you would start with pH 13 and then you would end with pH 4. Your equivalence point will still be the same. Your shape will still be the same. So it looks like that. Okay, I have a graph for you. I'll show you later, and it is in your notes as well. Okay, next we move on to strong acid and weak base. Okay, again, starting with your initial pH, a strong acid would be very, very low. So that's about pH 1. And then you're reacting with a weak base. That means in excess, you are measuring a pH of lower than 13. All right. So around 10, 11 is good enough for a weak acid, right? So you don't have to be specific. Okay, and then your vertical region, So this is the opposite of the previous example where we have a weak acid, strong base. This time our acid is strong. So that means our vertical region will be pulled down to the lower pH because this time the acid is stronger, right? So you just think of it as who is stronger, and then that person will pull the vertical region. What if they are both strong? Strong acid, strong base. So you have an extended vertical line. In a way, they are both trying to pull the vertical line. Okay. Here, your base is stronger. So your vertical line, vertical region is being pulled up to the basic region or alkaline region. As for strong acid, weak base, your vertical region will be between 3 and 7. Again, at the same volume, which is 25 centimeter cube, because that's how much you need for neutralization to occur at the exact amount. No more, no less. 3.5 to 7.5. Maybe I'll use this. 3.5 to 7.5. Okay, so I can't really see. But yeah, and then you just draw a smooth curve to connect them. Okay, so you can sort of see that your vertical region is pulled down, and that means your equivalence point, which is the midpoint of your vertical region, would be somewhere around 5. And that point is where neutralization is happening. But sometimes, you know, because it's a big change, it's a drastic change, and we cannot possibly identify or pin exactly where the equivalence point is. So we just take the middle point. Okay. Okay. Same idea like the other type of pH curve. Same thing as well. If we were to switch the position, this time I have an alkali in my conical flask. So that means my starting region would be a weak alkali would be at somewhere pH 10 or pH 11. Okay, and then I will end up with a strong acid, which will be at pH 1. So it would look like that. Well, not great. Let me, okay. The vertical region should be the same, like that. Yeah, I think that's much better. So imagine that as a vertical region, okay? The shape is the same. The initial and the only thing that's changing is the initial pH and the final pH. The volume must also be the same. That's why it is important for you to identify who is in the conical flask and who is in the burette. Okay, next is the only thing that is different: weak acid and weak base. So neither of them is strong to pull the vertical region. Actually, so that's why there is no vertical region in this type of reaction. Okay, here an example of a weak acid is ethanoic acid, and an example of a weak base is ammonia. Both of these molecules are organic molecules, so they are generally weak. There is a mistake in my graph. I think I copied the wrong graph, but yours is correct, I believe. It should start at 4 because it's a weak acid, and it should finish at 10 or 11 because it's a weak base. And the neutralization is happening at somewhere at 25. Okay, there's no vertical region because there is no sharp change. So something like that. Okay, maybe not, because it's like a nice gradual change like that. Okay, so what happens, because they are both weak, they change and the change in pH is also like gentle, okay, and really slow, right? That is all you need to know, okay? Now, in terms of indicator, later on you will see, because there is no vertical region, it's difficult to tell where the equivalence point is, although I know it is happening at 25 because that's my volume of neutralization, right? But the indicator would not be able to tell you this. So doing or carrying out titration for a weak acid, weak base reaction is actually not great because you don't know where the end of the neutralization is. All right. Next is showing you if I had a base in the conical flask and acid in the burette. Okay, so just to go through this roughly. Oh, it's not labeled. Great, then this is great. So I want you to label them, which is which. Okay, so I will number them A, B, C, and D. Okay, so this time we fill in the burette with acid and the conical flask with base, and I've labeled them A, B, C, D. So you will answer in the forms, which type is it? Is it a strong acid, strong base, or weak acid, weak base, or weak acid, strong base, or strong acid, weak base? So there are 4 types, right? Okay. Next is choosing an indicator. Select a suitable indicators for acid alkali titrations given appropriate data. pKa values will not be used. Now, indicator actually used to be in your A2 syllabus. Now it has been moved down to AS syllabus. So it should be as simple as possible. Okay, so if you see the pKa values of indicator in question, just ignore it. And also, if you are looking for questions that involves indicator, they will not be in the AS paper. They would have been in the A2 paper. Okay, so let's read about indicators. Indicators are substances that change color when they are added to acidic or alkaline solutions. So indicators must have different color in acid and then another color in alkaline. Okay, they can't have the same color. Otherwise, well, then they're useless to be an indicator. When choosing the appropriate indicator, the pH of the equivalence point is important. So this is what I was saying just now. We want the indicator to change color as close as possible to the equivalence point. So we give a range. As long as it falls in the vertical region of your pH curve, then that should be fine. So these are some of the common indicators that you would have to be familiar with. We've all used methyl orange, okay? At acidic region or at lower pH, methyl orange is red in color. We don't want that. At higher pH or at an alkaline region, it is yellow in color. Again, we also do not want that because these two are extreme colors. We want in the middle. Okay, in the middle, it would be the endpoint color of methyl orange would be orange, very pale orange. If you missed, so you would start, if you have acid in your conical flask, you would start with a red and then slowly turning into a peach and then turning into an orange. And then if you have excess, it will turn into yellow. Okay, so red or yellow is like a red flag for you. You don't want these colors. You want the one in the middle, which is orange. The pH range is the range at which these indicators change color. Okay, so that means below pH 3.2, methyl orange would be red. Above 4.4, methyl orange would be yellow. So orange, methyl orange becoming orange is only between 3.2 to 4.4. So you want your equivalence point to lie inside this range. Okay. Bromophenol blue is yellow below 2.8. Okay. And then above 4.6, it is blue in color, but the color that we want is light green. Okay. Or like sometimes dirty green. Again, your equivalence point needs to be situated between 2.8 and 4.6 if you are using bromophenol blue. Next is the bromothymol blue. Below pH 6.0, it will be yellow in color. Above 7.6, it will be blue in color. And when does your neutralization reaction end, or when is it complete? It is inside or between 6.0 to 7.6, and the color is also light green. Lastly is the phenolphthalein. I think this is also something that you are familiar with. Below 8.2, phenolphthalein appears as colorless. Above 10, phenolphthalein appears as a pink or violet. Okay, so I always tell you, once you get to pink or violet, that's already in excess. Okay, so the best thing is faint pink or light pink. Usually I would say the first permanent hint of pink. Okay, so you don't want to go really dark. And again, your equivalence point of the reaction that you're carrying out must lie between this range. The color of indicator changes quickly within the pH range, even on addition of half a drop. Okay, methyl orange change in color from red to yellow within the pH range of 3.2 to 4.4, whereas phenolphthalein change in color from colorless to pink within the pH range of 8.2 and 10.0. Okay, so for your syllabus, they only talk about your AS syllabus, they only talk about methyl orange and phenolphthalein. So how do we Oh, not yet. Yes, choosing the suitable indicator. So we want to choose indicator that has its pH range within the vertical section of your pH curve. So you need to remember your pH curve. You also need to remember your the pH range of your indicators. Okay. The reason for this pH range is because this is where the indicator will change color. So if the neutralization is happening there, because neutralization is change in pH, right? You go from acid to alkali or the other way around. And your indicator also need to change color at this point to say, hey, stop. You have to stop the reaction. Okay, I will show you an example of phenolphthalein first. Okay, so this looks like a pH curve of, since it's starting at 4, it looks like it's of a weak acid, and it finishes at 13, strong base. Okay, so it's of a weak acid and strong base, as you would imagine, because the base is strong. It pulls up your vertical region between 7 to 11 roughly, right? Phenolphthalein, the pH range of phenolphthalein, if you refer to your notes, is between 8.2 to 10. So this is range, pH range, sorry. It should be pH range at which phenolphthalein changes color. Okay, so as we know, neutralization is also happening at X equivalence point. Where H plus is exactly equals to OH minus. All right, so you would imagine the indicator when we are at pH below 8.2, we see a colorless solution, right? And then above 10.0, we see a pink or violet solution. That's why we want something in between, which is a light pink. If you're pink, you're already at this point, which is not too bad still, but who knows if you're already here. That's already excess in hydroxide, okay? If it's colorless still, then it will be here. You may not have reached the end of the titration yet, okay? Right, so that's phenolphthalein. You can use phenolphthalein for a weak acid strong base reaction. Oops. Methyl orange. Okay, so methyl orange, this is a strong acid because it starts at pH 1, reacting with pH 11, so that's a weak base. Okay. Right. So this time we choose methyl orange. Okay, why don't we use phenolphthalein? I'll show you. Phenolphthalein is between 8 to 10. So I'll just label. Can't spell. Basically, phenolphthalein will only change color at this point, and that is not your neutralization point. You are already in excess. You're in excess base or excess alkali, okay? So we cannot use phenolphthalein for a reaction that is between a strong acid and a weak base, okay? However, we can, so I'll just cancel that. We can use methyl orange because the range of methyl orange is between 3.2 and 4.4. So that's the pH range of methyl orange. Okay. And this is also where your equivalence point is. It coincides, oh gosh. It coincides where your indicator changes color as well as your reaction is complete. Okay, I hope that makes sense. Okay, that's how you choose your indicator. This looks like a complicated graph, but actually it is not. You just have to choose on which one you want to focus on. Okay, so say I want to look at strong acid and weak base. Strong acid, and then this is my weak base. Okay, so I want to choose an indicator that falls, the pH range of the indicator must fall in my vertical region, and that's methyl orange. Okay, if I'm looking at, let's say, strong acid, strong base. Okay, strong acid and then strong base. Now you notice that strong acid, strong base has an extended vertical region, right? So the answer is yes, you can either choose phenolphthalein or methyl orange because both of this pH range lies inside the vertical region. Okay, the only thing that is a problem is your weak acid, weak base, because there's no vertical region. It's simple as that. There's no vertical region, and also the indicator does not coincide where your equivalence point is. Basically, it's difficult to know where equivalence point is for weak acid, weak base, or you don't know when the end of the reaction is for a weak acid and weak base reaction. Okay, now with that, that's the last section or the last part of this topic. Next, I want you to fill in your pH curve. In your notes, there is a box that says suitable indicator and its range. Okay, so I don't have it here, but there should be on page, if you look at page 27 and 28, On the right side of your graph, just below the dotted box, there is a box for you to write down the suitable indicator and its range. Okay. How do you do this? You just choose the indicator and the range that is given in this table, on this table. Okay, except for weak acid, weak base, it has already been mentioned on your notes that there is no suitable indicator to determine the endpoint of this reaction accurately. Now, you can use an indicator, and there will be color change, but that will not be as accurate as other type of reaction. Okay. All right, so that is the end of topic 7. As usual, you will fill in Microsoft Forms. The link can be found in the description box below. Thank you so much. I will move on with the next topic in the next session, okay, which is topic 8. Assalamu alaikum and thank you everyone.